Hi, everyone. It's a pleasure to be here. Thank you, Sebastian, for the very kind introduction. Thank you for my committee members for also taking the time to be on this call. And it's great to see some familiar faces and also some new faces here in the audience today. So I'm going to begin talking about my PhD thesis, which is on active vision and how we can develop systems for autonomous aerial cinematography with learned artistic decision-making. So on a very high level, the topics I'm going to go over today are how we can develop agents that can interact with humans and act with purpose in wild and dynamic environments. And even though the application I'm going to focus on today is that of aerial vehicles for cinematography, many of the concepts and ideas that I'm going to describe today can also be applicable to other domains, from self-driving cars to manipulators and even to virtual agents such as in games and simulations, for example. But the reason why I'm focusing so much on aerial vehicles is because they are extremely versatile platforms that allow us to explore many interesting research ideas and problems in this domain. And we can think of drones as basically being flying cameras. And over the past few years, we have seen how drones can act as a tool to augment human creativity and expressiveness in many scenarios. Here you're seeing some examples of professional footages that were taken using drones. And they allow us to achieve viewpoints that have never been possible before with the use of traditional technologies. And it's not only movie productions that active cameras are reinventing, but they're also touching many other applications, from games and entertainment to virtual reality. They change the way we can record social events and sports productions, and they're even touching the area of defense and security. However, there are many challenges when we try to deploy, especially these manual cameras, in either physical or virtual scenarios. The first set of challenges is related to the interface between the human operator and the drone. Usually we have quite unintuitive interfaces that are based on joysticks or on keyboards that are full of controls and knobs that make it very hard for a human to intuitively maneuver the camera in space. Also linked to this first challenge is the fact that because we have such unintuitive interfaces, we usually require multiple operators to control these drones, which ends up creating a very expensive operation. For example, in some professional movie scenarios, we find up to 3, sometimes even more operators controlling a single drone, where one person controls the movement of the vehicle in space, another one controls the movement of the gimbal camera, when you have a third person that is only controlling the focal distance of this camera. So that's a very expensive process. And third, we have a factor that is often neglected, but also plays an equally important role in this operation, which is the fact that it takes many years for a director or for a cinematographer to learn how to master the art of movie making. And they usually go to filming school. They take many years of apprenticeships to be able to not only control the camera smoothly in space, but also to be able to tell a story using images. And taking all these challenges into account, the overarching goal of this thesis is to use AI to empower any individual with the full artistic capabilities of aerial cameras. And to do that, we have to model 2 major classes of problems. Problems related to the interaction between the camera and the environment it's operating at, and also challenges related to the interaction between the camera and the human operators. So as for the first challenge, when we think about the interaction between the camera and the environment, we have to consider 2 main threads of processing. The first one has to do with the context of the scene. So we have to identify who our actor is, and also what is the future forecast of the actor's movement in space. That also depends on the semantic context of the scene and the classes and the types of obstacles that we're seeing in the environment. We also have to consider the scene geometry, especially if we're dealing with physical cameras. We have to map obstacles in the environment because we need to avoid colliding with them and also avoid occlusions that those obstacles may generate on the image that we're producing. And for the second set of challenges related to the interface between the human and the camera, we absolutely don't want to have a very complex interface that is full of buttons and knobs that make it unintuitive for a person to control our cinematographer. What we want instead is to have a human-driven interface where a person can express intent in a very intuitive manner. And intent can be expressed in many different ways. We can express intent in terms of parameters. For example, if you say that you want the drone to circle around you at 30 degrees per second. We can express intent in terms of tasks. For example, if you say that you want this drone to follow you on your bicycle as you go along a trail. And we can even think of more complex types of intent expressions, for example, using emotions. If you tell a drone that you want to make a very exciting clip, then the drone has to process this command and find the most suitable camera movements. We also find very interesting related works that touch many different aspects of this problem. First, we find works related to virtual cinematography, which is the movement of cameras in space. We also find papers on automatic movie editing using either style-based rules or any other rules that are applicable to our particular application that we have. There's also a vast literature on planning, vision, and mapping system for robotics, which we're going to heavily reference during this talk. And finally, we have papers that are related to learning artistic concepts and interfaces between cameras and humans that are going to be quite relevant to what we are trying to do. And our work lies at the intersection of all these disparate domains of knowledge, and we're going to take advantage of many of the concepts that were defined in previous works. So now I'm going to give you an outline of what this presentation is going to cover. The first thing I'm going to talk about is the problems that relate to the interaction between the camera and the environment. And specifically, I'm going to explain to you how we can close the loop between planning and perception systems. Second, I'm going to talk about the interactions between the camera and the human operator, and how we can learn artistic and expressive meta-policies that shape the movement of this camera in space. And third, I will describe the interactions between the camera and a simulated environment, because oftentimes we use simulators to train many of the models that we deploy in real life. And specifically, I'll focus on how we can transfer state representations from simulation to real life. So without further ado, let's get into the first topic. I want to begin this section with a cartoon. And even though this cartoon is a little bit silly, I think it illustrates some important points in robotics. So here we have a robot that is trying to go from point A to point B. And instead of taking the very logical, simple, straight line path from A to B, this robot is actually going to the back of the room. It's doing loops and going around the entire room. And while it's doing these crazy motions, its fellow robots are watching all of this happening. They're clapping, and they say that even though this path is suboptimal, it has flair. And the reason why I think this cartoon is interesting is because it brings up a point that for many applications in robotics, and arguably for almost all the applications we care about, we cannot define them by a single, simple objective function. And in fact, we have to balance multiple objectives that compose this harder to define task. And this idea is especially true in the case of cinematography. When we think about flying a drone in space, we're not only trying to go from point A to point B as fast as possible, but we're actually following a target. We have to keep this person on our image at all times. And while the drone is moving in space, we have to obey a series of cinematography constraints and rules during the motion of the vehicle. And to try to understand what these constraints are, I think it can be helpful for us to take a look at what happens in a professional movie studio production. So here you're seeing some scenes from the movie 1917 and how it was produced. And you can notice how complex the process of producing a movie is. You know, how many people are involved in this operation, the types of equipments, of hardware that is used to manipulate the camera in space. And in fact, we can break down the process of a professional movie production into three phases: the pre-production, production, and post-production cycles. And when we think about automating a cinematographer, we're not trying to automate every single task involved in these three phases, but we're looking at a few particular tasks. For example, creating the shooting script, inferring the actor movements, looking at the camera placement, the storyboard, and even to some degree, the act of editing and cutting scenes. And before I get into the mathematical definitions of how exactly we frame this problem for our application, I do want to show a video just to illustrate exactly what's happening when we talk about filming and cinematography in the wild. So here you're seeing some footages that were captured fully autonomously using our system. And you can see how our drone is autonomously tracking this person who is running down a trail. It's avoiding obstacles on the left and right sides of the trail. And the way it works is, first, we get a bounding box that tells us where the actor is on the image. We estimate the heading direction of this person, and we forecast their motion in space. We also have a LiDAR on the system, so we're capturing points, thousands of points of the environment per second. With this, we build a map, and we use this map to plan feasible motions for the camera that avoid collisions and occlusions with obstacles in the environment. We can also do shots with multiple types of actors. So here you see people walking, running, and on bicycles, for example. And here you see a third-party perspective of our system in action. So we had a drone filming a drone that is filming the actor. And you can see how our drone that is a little small in the back of this footage is aggressively tracking the person who is trying to run away. Here you see some details of our heading estimation module. And by knowing the direction that the person is pointing, we can do something like a frontal shot, which is a very complicated shot type to do if you're flying the drone manually, because you always have to correct for the positioning of the person. We can do multiple types of shots and even combinations of different shots. So here you see a circling shot around the actor. And we can follow multiple types of actors. So here you see a relatively high-speed chase with a car. So as you could see in the movie, our work offers a comprehensive solution to many of the tasks involved in the production of a movie, from the act of making artistic decisions autonomously to the vision system, mapping, and then all this information is taken into account for the motion planning system to compute feasible trajectories for the camera. And the very first thing I did in this project was, before trying to mathematically defining what we want out of the camera movement, I tried to understand the way in which movie directors think about camera positioning. So to do that, I read several books on cinematography, and I even spoke with several professional movie directors, and some of them might even be on this call right now, to try to distill the minimal set of parameters that guides the position of the camera. And we find three main parameters: the shot scale, so that's the distance to the actor, the line of action angle, which is the horizontal angle of the camera, and the tilt angle that shows us the vertical positioning. And by using these three parameters, we can analytically define a desired trajectory for our shot. And naively, we could just follow this trajectory at all times relative to the motion of the actor to obtain the perfect shot for our scene. But the problem is that this shot can oftentimes, if we're flying on real-life environments, it can oftentimes be in collision or be too close to obstacles. So what we try to do is to find a quadrotor trajectory that is as close as possible to this desired shot, but is still safe and feasible. And to do that, we develop a motion planning system. And for our application, we have a few requisites. For example, we want to have a relatively long time horizon because we want to be able to avoid myopic behaviors, such as getting stuck close to a tree or a building and not being able to find a trajectory around it. And we also want to plan trajectories at relatively high frequencies, because we're dealing with very dynamic scenes. If we're filming a person who is running, they may change directions very suddenly. And we want to be able to adapt to those changes and find new motions for the camera. And mathematically, the way I define this is as a minimization problem, where the optimal trajectory is the one that minimizes a set of cost functions. And specifically, we have a weighted set of costs related to the smoothness of the motion, obstacle avoidance, occlusion avoidance, and also the shot quality. And the actual algorithm that I used to perform this optimization is an adaptation of the CHOMP algorithm, which was developed by Nathan Ratliff, who is also on this committee. So now we can get into the details of each one of those cost functions. First, for the shot quality cost, so the way we define it is quite intuitive. What we're trying to do is to minimize the distance between the quadrotor trajectory and this desired trajectory for the shot. And we define this as a L2 norm between both trajectories in space. Next, we have the obstacle avoidance cost, and this is also quite intuitive. What we try to do is to bend our trajectory away from obstacles. And to do that, we use the concept of a side distance field. So for each point in space, we know the distance to and the direction to the closest obstacle, and we bend our trajectory in the opposite direction. And next, we have the occlusion avoidance cost. And this cost is extremely important to maintain the quality of the footage that we do in the environment. And our work was the first one to introduce a differentiable cost function for occlusion avoidance. And the reason why this matters is that even though the concept of occlusion is binary, that you see or you don't see the actor, we're using an optimization-based framework to find our solutions. So we need to have gradients for this cost function. And the way we do this is we first think about a particular moment of time where we have a position for the drone and for the actor. And we can think of a light ray that goes from the camera to the person. And we try to minimize the penetration of this light ray inside of obstacles in the environment. And we have to do this not only for a single instant of time, but also for the entire duration of this trajectory. That's why we have the cost defined as a double integral over this 2D manifold that connects the camera and the actor over time. And here we can see some results, how this looks like in a 2D simulation. So even though we initialize the path of the camera above this obstacle, the occlusion avoidance cost bends this path downwards so that we have visibility of the actor at all times. And next we have some 3D results where you can see the comparison between a drone that is only using obstacle avoidance versus occlusion avoidance. And if it's only trying to avoid obstacles, even though we're not crashing with anything, with this mountain, we're going to oftentimes lose view of the actor. While if we use occlusion avoidance, we find a path that is smooth above the mountain, where we always have visibility of the actor who is on the other side. And now that you understand how the motion planning system works, I do want to give some more details on the mapping and the vision subsystems from our architecture. As for the mapping subsystem, what we have is as you saw in the video before, we have a LiDAR that is capturing thousands of points of the environment per second. We register these points based on the drone's coordinate frame, and we build an occupancy grid that tells us for each cell in space if this cell is occupied, free, or unknown, if we simply have no information about it. And using this information, we also build incrementally a 3D truncated signed distance field, which is the information that is being used by the motion planning system to avoid collisions and occlusions with obstacles. And as for the visual system, as you saw in the video before, we're getting the bounding box and the heading estimation vector of the actor on the image plane. And once we get that on 2D, we project this information into the 3D word reference frame onto the map that is being built by the LiDAR in real time. And that's how we get the actor's 3D position in the word. And even though all the concepts and theory that you saw being developed so far were focused on a scenario that had a single actor and a single drone, in our latest paper for ICRA this year, we extended these ideas to a multi-robot scenario. We did have to add two cost functions in addition to what you saw before. So we have a inter-UAV visibility cost that tries to minimize how much one drone sees another during the footage, because usually, in most cases, you don't want one drone to see, to have the other drone on site while you're filming an actor. And we also have a shot diversity cost that basically tries to repel the cameras in space so that we maintain many diverse viewpoints while filming the same subject, because there's not a lot of value of having two cameras that are basically at the same viewpoint. And here you can see some, so this is a autonomous footage that was captured of a soccer player in an unscripted scenario. And you can see how much more interesting this combined footage by combining two drones is in comparison with the case if we were only filming this from a single viewpoint at all times. So now I want to wrap up this first part of the talk with a few key ideas related to the interaction between the camera and the environment. The first key idea I want to mention is that when we're dealing with a very complex task, it can be extremely helpful for us to break down this task into multiple objective functions. And this is especially true in the case of cinematography, because we have it's very hard for us to define a single simple objective that is able to comprehend the entire complexity of the task that we have in hand. And the second key idea is that what we're trying to do is to have active sensing and effectively close the loop between planning and perception systems. And we do this with the use of special purpose cost functions such as occlusion avoidance that allows us to not only passively processing the information feed or passively recording the images that we get from the camera, we're actually planning ahead and positioning our camera in places that maximize the quality of the footage that we're taking. And I think it's important to emphasize here that even though these concepts were developed, especially occlusion avoidance. The way we showed here was very much focusing on the application of cinematography. The same concepts can be applied to other domains as well. Let's take the case of a self-driving car, for example. Now, if this car is trying to do a right side turn and the right side is occluded by bushes or trees, us as humans, if we were trying to do this turn, we would naturally slow down because we can't see what's on the right side. And I think it's also important to explicitly encode this idea of active sensing into other domains as well. And the same concept applies to even manipulators, for example. Let's say that we're trying to grab an orange in a very occluded shelf on a fridge, but the orange is covered by a lemon and we have other fruits around it. Instead of just trying to plan, very often what we do is we just try to plan with the information that we have right now. But I think it's also interesting to think about applying these concepts of occlusion avoidance so that we can move cameras in a way that we maximize the quality of the sensor readings that we will have in the future as well. Okay, so now I'd like to go to the second part of this talk where I'm going to describe the interaction between the camera and a human operator, and specifically how we can develop artistic and expressive meta policies that are going to shape the behavior of our camera. The first thing I want to do here is to first define what an interface is. So an interface is a tool that allows operators to express their intent towards the robot. And there are many ways in which you can build an interface. As you saw before, we can have interfaces in the form of joysticks or keyboards, which are very direct and can sometimes be quite non-intuitive depending on how complex your robot motion is. We can have interfaces based on parameters, such as velocities, distances, and angles that the operator sets, and then the camera can autonomously execute those, which is what we're using what we were using in the first part of this talk. We can also have more complex interfaces, for example, based on semantics. You can tell the drone to do some command using natural language, and then this command can be interpreted and sent for the robot for execution. And I'm going to describe how we can develop such a system next. And on a more extreme scenario, we could actually cut the human altogether from the interface and have a robot that plays the role of the movie director and that chooses which kinds of shots are more suitable, more appropriate for each context of what's happening in the scene. And I'm also going to describe how we can take a first step to try to learn such a system. So as you probably are wondering right now, there are many challenges that make it difficult for us to try to learn an intentional interface. And one of the major problems is that commands often have multiple interpretations, especially if we're dealing with semantics or if we're trying to learn from human data. And this is hard because there are also infinite ways in which you can capture a scene. So we're dealing with a very high dimensional space. Now we could be anywhere relative to the actor, and the drone's position can be even changing over time. And to make things even harder, emotions vary from person to person. So let's say if I'm trying to make a movie that is very exciting, what I find exciting may be not as exciting for somebody else who's watching the same movie. So thinking about these challenges, the first work that I'm going to talk about is one of our submissions for ICRA this year, where we learn a semantic user interface using that uses commands in natural language between the user and the camera. So before flight, we have the user that sends a command, such as they want to make a very exciting clip. And then this command is processed by the semantic interface and sent for the robot for execution. And here you're seeing a fully autonomous clip that was captured with our system that was in fact trying to maximize how exciting this clip looked. And it also helped a lot that we had a co-author who can do backflips, so this made the movie even more exciting. So more formally, what we're trying to do here is to learn a mapping between shot parameters and emotions and vice versa. So let's say we have a video. This video has the camera moving in some pattern that we can say that we have the features of this camera trajectory that are given in terms of some shot parameters like velocities, distances, and angles over time. And what we want is to learn a function f that maps these parameters to a emotional descriptor vector that tells us, if we had somebody watching this movie, like how would they rate this footage emotionally? And we also are interested in the inverse function, f-1, that given a set of emotional descriptors for a movie, how do we actually find the camera trajectory that would generate the movie that we intend in the first place? And one of the hardest things about this problem is obtaining labeled examples, obtaining data. Because even though we have a lot of videos online, YouTube has, I don't know how many millions or billions of videos, the information we have there are things like the number of views, number of likes, but we don't really know, how people were feeling when they were watching those movies, or on a very granular level. So the first thing we had to do for this project was to build a diverse data set with with hundreds of footages taken from different viewpoints. And we used crowdsourcing to obtain user evaluations, emotional user evaluations for each one of those clips. So we had thousands of people rating the movies that we collected. So the first thing was, producing this very large quantity of different videos. And to do that, we had a particular scene of a person that was going around a suburban environment. And for the same exact scene, we recorded it from hundreds of different viewpoints. And after we had this data set on hand, we obtained labels, emotional labels for the videos. And to do that, we used pairwise comparisons. So we showed each user 2 videos at a time, video A and B, and we asked the question like, which video is more exciting, which video is more interesting, and they had to tell us if it was the one on the left or the one on the right. And the reason why we're using pairwise comparisons is because humans are really bad at giving absolute scores for subjective quantities. So if I ask you, from 0 to 10, give me like a score of how exciting is this clip, there's going to be a huge variance of scores between people. And what's even worse, the order in which we show videos for the user can dramatically change the ratings that they're going to give. And so the information of pairwise comparisons is much more reliable. And once we collect all this data, we aggregated the results, and we traced correlations between different emotional scores. And we found some things that are quite intuitive here. For example, videos that are rated as being very exciting, it has a very high negative correlation with being calm. So that's pretty intuitive. Exciting videos are usually not calm. And we also find other patterns, such as exciting videos are usually also rated as being very interesting. And we can find all these patterns between all the different emotions here. Something we also did was to treat these emotional correlations as distances between emotions. And we plotted this information in 3D to try to come up with a 3D emotional feature space that tell us which emotions are clustered closer together or further away. And something that was quite interesting in this project was that we found that our emotions can actually span a 3D space, and they do align with the major emotional axes of arousal, valence, and dominance, which is how a lot of literature in psychology classifies human feelings and human emotions. So it was very exciting to see that our experimental data validates what we expected from literature in psychology. We also have some other interesting insights from this problem. We found that it's much easier to learn a mapping from shot parameters to emotions than it is to learn the inverse model from emotions to shot parameters. And the reason is that if you think, for example, that you're trying to do an exciting clip. There are many different camera positions that can render a clip that is very exciting. Maybe some of them are very close to the actor. Maybe some of them are further away, but traveling very fast with the camera. And that's why this is a one-to-many mapping. But the inverse does not necessarily hold. Usually, if you start with a particular camera position and you do variations along this position, you're usually going to find very similar emotions. And we also evaluated our models. For example, here you can see we're evaluating the model that predicts emotional scores from videos. So we have in orange our predicted values, and in gray, those are the crowdsourced values that we got from the user study. You can see for this emotion of how establishing a movie is, how our scores compare to the ground truth values, and you can see this for all the other emotions as well. And even though there is quite some noise in our predictions, it was very exciting to see that we are able to encode such subjective concepts into a learned model from data. And what's arguably even more interesting is the inverse model that we evaluated. So how can we generate shots that have particular degrees of emotional expression? And here we can actually pick even the intensity of the emotion we want to generate. So we can go from less establishing to more establishing shots. We could have potentially linear combinations of multiple emotions together. And we can generate videos that have that particular rating, emotional rating. And finally, we get these clips that were generated in the simulator, and we apply the policies for real-life flights. So here you're seeing a soccer player, and I think we're trying to maximize how interesting this movie is. And the choice of shot from the drone was to do a right side shot, kind of close by, changing from the back to the front of the actor over time. All right, so far we saw how we can devise an interface that uses semantics to allow a user to express their intent towards the camera. And now I want to get into a second topic that is, what if we actually didn't have a human at all in our interface? And what if we trained a robot to act as a human director to give commands for to maximize the quality of the movie that we're producing? Before I get into the details here, I do want to make a clarification of what we are trying to learn and what we are not trying to learn. We are trying to learn the very high-level actions. So it's a policy that tells us roughly, where should our camera be in space. For example, in the beginning, at instant T1, the drone is in the back of this actor, and then the camera thinks, oh, I think in the future I should do a left side shot, and then it moves to the left side, and then it says, I should do a frontal shot, and then it moves again. But this happens every few seconds. It doesn't happen, like every millisecond, for example. So what we are not trying to learn is the low level actions. So all the dirty work of the optimization and trajectory tracking is being done by the systems that I presented in the first part of this talk. We're not trying to learn that. And mathematically, when we think about this problem, we see that it's time dependent. So we have to treat these choices of shot parameters like a sequential decision-making problem, because the choices that we make at initial time steps are going to influence the position of the drone and the types of states that we will encounter in future time steps. So mathematically, what the optimal set of artistic choices is the one that maximizes the quality of the movie that we're producing, and we define quality as the summation of a artistic reward over time. And for now, I'm going to leave this artistic reward a little ambiguous, and I'll explain what it means on the next slide. But something we can get out of this definition is that we can model this problem as a MDP, and we can say that a optimal policy that chooses the artistic parameters is one that maximizes the expectation of artistic rewards over time. And to solve this MDP, we use an approximate solution with deep Q learning with a human in the loop. So we have a deep Q function approximator that takes into account a local height map that gives us the information of which obstacles we have around the drone. We also input the current shot mode, which tells us where the drone is right now relative to the actor. And we have a shot repetition count that tells us for how many time steps we have been doing the same action. And the output of our network are the Q values for each one of the actions that we can take. We can do a frontal, back, left, or right shots. We have 4 possibilities. And finally, what's missing is the reward function. So our reward is coming from a human evaluator. So we had a lot of grad students eating pizza in a basement for a few hours, and they were watching these videos, and every few seconds they would rate the quality of the movies that they were watching. And that's the information that we used to train the network. What's interesting here is that the policy is able to learn quite intuitive and human-like behaviors. So we see that it tends to avoid structures because usually the drone can get stuck, collide with structures, or have its view occluded by a building or trees. And we also see that, for example, in a corridor environment, the drone tends to very much stay behind or in front of the actor while the actor is surrounded by houses. And then once the actor comes out of this corridor, it tends to go to some other position. And we take this policy that we're trained in simulation and we deploy them in real life. So here you're seeing a movie that has been captured autonomously using the system. Initially, it's doing a left side shot, but then because there were a bunch of trees, it goes back to the back of the actor. Once there's a clearance, it goes back to the left. And something else we learned was that the policy tends to switch shot types often, but also not too often, sort of to maintain a balance between a movie that is too boring, from the same viewpoint at all times, versus being too confusing for the viewer. So to wrap up this second part of the talk, I want to bring up some key ideas related to the interaction between the camera and the human operator. First, we use multiple layers. I think it's very important to use multiple layers of control when we're dealing with a very complex problem. So, for example, what we saw here is that we're breaking down this very complex problem into a high level and a low level motion policy. The high level makes this rough artistic decisions. The low level does the actual optimization and trajectory tracking. And the second key idea is that we were in fact able to learn very subjective human concepts using different machine learning techniques. So we saw how we can use imitation learning to augment human expressiveness using semantics. And we also saw how we can use reinforcement learning to, in fact, replace the human in the loop and try to learn a creative artistic policy. And here again, I think it's also important to emphasize that even though a lot of these concepts that I showed are very much focused on cinematography, they can also apply to other domains of robotics. For example, if you think of a self-driving car, a self-driving car is not only trying to go from point A to point B, but the way in which it does its motion is also very relevant for the task. So we as humans are very good at capturing if, even from a few seconds of observing some driver, we know if they're being very aggressive or very conservative. So this has to do with the way in which you perform the motion, not so much as going from A to B. So I think it's very, very interesting to see how we can explicitly use some of these techniques that I showed to encode styles or emotions or emotional behaviors into the motion policies of other agents. And again, the same concepts apply to other areas such as manipulators, where let's say if we're trying to handle a cup of coffee to somebody, we're not just trying to give them the coffee as fast as possible, but we want to make the motion trustworthy, and people have to be able to understand the motion and trust the robot that they're interacting with. All right, so now we're ready to cover the third and last part of this presentation. And I'm going to talk about how we can design robust models that can transfer representations from simulation to real life. So to just motivate this topic, I have a quote from Yogi Berra. He was a famous baseball player who had some very funny quotes. And he once said that in theory, there's no difference between theory and practice, but in practice there is. And I took some artistic liberty here to modify this sentence for the context of robotics, to say that in theory, there's no difference between simulation and practice, but in practice there is. And what I mean by that is that even if we try to use the best simulators we have out there, we're always going to have a gap between physics, between shapes, colors, textures of how things look in a simulator and real life. And you saw in the past couple sections of this talk that many of the models that we train in simulation were deployed in real life directly. And sometimes this can lead to small errors, but sometimes they can be quite large errors. And the goal of this section is to try to explicitly take this gap into account and train models that do consider transferability to real life. And the application I'm going to be focusing on is that of drone racing. So basically we have drones that are going through this obstacle course, and they go through these red hoops in space. and they have to do that for as long as they can without crashing. There's a lot of work in literature that explores this idea of scene-to-real transfer and deploying visual model policies. Some of those papers, they train models using only real-life data, which is possible, but it can be quite expensive to collect all this data. Some of them train mostly in simulation and only fine-tune with a little bit of real-world data. We also see works that use a famous technique called domain randomization, where we query randomized textures, colors, and shapes of obstacles in the environment to try to learn a more robust representation. And we also see discriminative methods that explicitly try to lower the gap between simulated and real-life representations. But in the work that we presented at IROS last year, we take a slightly different approach. So we're trying to train a visual motor policy here that takes as input a image, RGB image, and our output is a velocity vector. And instead of training a black box end-to-end network here, we're actually splitting up this network into a few components. We have a feature encoder, we have a latent representation, and a control policy. And our goal is to train a representation that, even though is only trained in simulation, can work well with real-life images. So the key idea that we use for training this representation is to use multiple modalities of data. So here you see part of our architecture. We have this input image that goes through an image encoder, and it is compressed to a latent space Z. And we use a standard variational autoencoder architecture to reconstruct the original image using an unsupervised loss. What we also put in this latent space is a second modality that comes out of the same latent space that tries to reconstruct the pose of the gate that we're seeing relative to the frame of the aircraft. And during the training process, we backprop both these losses simultaneously through our networks to try to train our image encoder that trains our representation using multiple modalities. And by using this method, we can obtain interpretable and even disentangled features. So just so you have an idea, here I am showing the visualization of our latent space. And out of we have a feature vector of size 10. And you can see how the first 4 features are actually directly related to physical attributes of the scene. The first one has to do with the distance to the gate. So you see how the size changes. The second one has to do with the horizontal position of the gate. The third is the vertical position. And the fourth is the rotation of this gate in space. And something else we get out of this derivation is we have a smooth and continuous latent space. So you can see here we are interpolating between 2 images. We have image A and B, which we're taking in a real-life drone racing course. And we're offering the interpolation between A and B in the latent space, both in terms of imaginary images and the imaginary positions of the gates that they would be in intermediate configurations. You can see how we can visualize these intermediate positions quite well. So it shows that our latent space is in fact learning the right things and it's smooth. And finally, we can use this policy trained only on simulation, and we deploy it in real life. So you can see here, this is a fully autonomous drone racer that is going through this obstacle course. And something else that is interesting about this derivation is that since we don't have a black box, we can visualize how things look inside of our architecture. So here on the bottom, I'm plotting the expected poses of the gates that we see on the image from the latent space. And we can see that it closely resembles the original shape, the S shape of the original track. So if something fails in a system, we can actually get an understanding of where is it failing, and is our perception system failing, or is it something to do with the control policy? And also, during deployment, we had some days where it was snowing quite heavily here in Pittsburgh, or we had very strong winds. And we saw that surprisingly, the policy, even though it never saw any of those behaviors like snow in the simulator, we were in fact able to do reasonably well in the real life racing course. So to wrap up this third part of the talk, I want to again bring some key ideas related to the interaction between the camera and a simulated environment. The first idea is that by using multiple data modalities, so multimodal learning can really help when we're trying to transfer policies from simulation to real life. And even more specifically, by employing a common representation between multiple modalities, this tends to avoid overfitting to a single one of those modalities in the simulator. In machine learning terms, you can think of this as the use of multiple modalities regularizes the training space, so we tend to avoid overfitting. And I think in the future, it would be very interesting to explore, beyond images and poses, explore multiple other sensor modalities, such as GPS signals, sound waves, point clouds, as possible sensor inputs to try to train a common representation for our as a latent space. And now I do want to take a step back and think about the original goal that we set at the beginning of this thesis. So our original goal was to use AI to empower any individual with the full artistic capabilities of aerial cameras. And through the course of this talk, we've seen how we can use special purpose motion planning systems to create dynamic cameras that are able to, in a very agile manner, interact with obstacles in the environment. We've also seen how we can use machine learning techniques to create intuitive interfaces between the human operator and the camera by augmenting the human semantics. And we've also seen how we can try to learn creativity and try to understand the role of the movie director in a scene to deploy these cameras and have them be creative by themselves. And specifically, we saw how we can group these categories of problems into two main domains. The first one being the interaction between the camera and the environment, and the interaction between the camera and the human. And throughout the course of my PhD, together with my collaborators, we have published a large body of work in several robotics conferences and journals that exploits many aspects of these interactions of the camera and in the context of cinematography. And before I wrap up, I do want to bring up a few open questions that follow up from my work. The first one is that I think we're barely scratching the surface of applications that are possible with the use of dynamic aerial sensors. So I think we can go much beyond simply recording videos of what's happening, but it would be very interesting to actually also reconstruct scenes in 3D in time. Here we have an example of a video from the CMU Panoptic Studio. So that's a collection of hundreds of cameras that sits in the basement of the robotics building at CMU. And by using the system, we can reconstruct scenes in a lot of detail. But the problem is that the system is static. It's in the basement of a building. So I think there's a lot of space for us to explore the concept of using multiple cameras to reconstruct scenes in the wild. So for example, reconstructing the movement of animals, the movement of humans, for sports medicine, for animal preservation, for example. There are many applications that could be used for this. And a second open question that follows from my work is the idea of learning robot styles. And we've seen, very focused on the context of cinematography, how we can try to express emotions or express styles in the patterns of the movement of this vehicle. But the same ideas could be applied to many other domains, such as autonomous vehicles, manipulators, and even virtual agents in games and animations, and even in a more extreme case for agents that don't even necessarily have a physical body to express their actions. Finally, I want to thank my collaborators and my committee. So there are a lot of people at CMU, Microsoft, Facebook, and other universities around the globe that played a very important role for all these projects and papers. And I want to thank my committee members for all the valuable feedback they've given me over the past year and longer. So yeah, with this, I'd like to conclude my presentation, and I'll be happy to take any questions you might have.
Thank you. Okay, so maybe let's, so I think traditionally we start with the external committee member. So maybe the cat wants to ask the question first.
I just asked her and she's okay. But yeah, I can ask some questions. One is a high level question. You presented basically two types of things, sections 1 and 2, and then section 3. For both of those, I'm curious what your take is on what's missing currently.
I think that I think I'm just barely scratching the surface of many of those problems. For example, maybe on the first part, when we think about the interaction between the camera and the environment, I think that segment was I think there's more literature on this area. I think that's a segment that is much more mature, much more developed in literature. Because we can't have robots that don't collide with things. I think both in academia and industry, people are making very rapid progress in this domain. So I would say that looking at the future, I would be less worried about that area. I think where we have more open problems is the area of collaboration between the camera and the human. So this idea of styles, like what I showed was, for example, augmenting human semantics. I was looking at a very specific scope of how we can represent emotions or emotional styles for the movement of the cameras. But there are so many other problems that we can look into this domain. Like how can we have more complex behaviors? The behaviors I was looking at I was only doing very short clips, like a 20-second, 30-second clip, using those emotions. But how can we have longer clips that express a larger, more complex type of emotion for the user? Now, how can we make a 2-hour movie that expresses some particular emotion? So I don't know if I'm answering your question directly, but I think overall on the second segment, there's a lot more work to do.
Mm-hmm, mm-hmm. Kind of following up on that, one thing, just thinking about this system as used for the context of the problem that you're addressing, which is cinematography and directors being able to use it to create more easily create movies with particular emotions and stuff like that. Directors often have a language that they use to say like how do they want to modify it or how do they want to establish a shot and stuff like that, how they communicate to the cinematographer. I'm curious from your perspective, how might you go about either using some of this or reframe the problem so you can more semantically connect it to that sort of language and potentially even like use how they direct cinematographers in real life as training data or something like that?
Yeah, it's a good question, and I think I can give kind of a three-part answer. One of the places where I tried addressing this language of the movies was in that first part of the talk, where on that first part, the interface between the human and the camera was via parameters. And I tried to look at what are the parameters that a movie director actually uses in practice to think about the camera positioning, and those were those three: the shot scale, the line of action angle, and the tilt angle of the camera. So this came from actual books in cinematography and from discussions that I had with directors. So this was one way. The second way in which I tried to capture this language of the movies was in the vocabulary that I used for learning that semantic interface. So the words, the specific vocabulary that I put there, those seven emotions, 7 words, were not like random words. I particularly chose words that people use when referring to the vocabulary of shots, either in movie reviews or in the context of a movie production. But I think in the future, it would be very interesting to see how there are many concepts that I'm not exploring in this work. I think for a lot of the much higher level vocabulary, like how do you make a dramatic movie? I think this is expressed over many more shots. and this is something that I'm not capturing at the moment, and also has to do with your previous question. I think that's an area for future research as well.
Mm-hmm. Okay. Yeah, I think I'll stop there for now. I have a few more, but we can come back.
Yeah, thanks. Who would like to go next?
I can go next, Basti.
Okay.
Hey, Rogerio, congratulations. It's a great body of work. I think it's gratifying to see not only strong theoretical contributions, but also real-world robots and real-world field studies. Well, congrats again. The question that I have is really trying to get to the whole process of being an artist. So when you think of being an artist in any discipline, there is a skill component and there is the artistic creation component of it. So for instance, when you're learning to play musical instruments, probably you're spending a lot of time just learning the skill. And once you have enough skill, then you can start to speak that language. Same with many other domains. And I want to hear from you, like all this body of work, where do you think in the spectrum of just learning the skill versus ability to create something truly artistic is your body of work lying on?
And you have a very good point, and it's something that we like struggled a little. So my answer is so in terms of the techniques that we use to learn these models. So we're using machine learning, and machine learning is based on learning from a data set. So I would say that what we are doing is trying to kind of average human behavior, learning average human behavior in terms of like how humans deal with those types of artistic situations. So in the case of the robot movie director, one of the segments of my talk, we are trying to learn on average what a good movie, a good quality movie looks like what a on average interesting movie looks like.
Yeah.
So I don't think you can say that we're being creative in the sense of creating something new. In the sense of the other part of my talk where we had the emotional descriptors, I think that is an area where we could potentially have some creativity, because we can devise linear combinations of those emotions, and we could in fact create a shot that we don't see in the data set, but that we know that statistically it might have that expected emotional expression, but we don't necessarily have to have that shot on the data set. So I think you have a little bit more freedom there. But
okay.
Yeah.
Yeah. Just a follow-up question. I think it's a very difficult question. I completely understand, but I just wanted to get a sense of how do you see it. One thing also I observe in this body of work, it's primarily driven by data, primarily driven by learning-centric techniques. And I want to just ask you, what role do you think symbolic approaches might have in actually solving the problem of creating art, or being artistic with cinematography here? What's your sense of how powerful or how useful the symbolic approaches might be, or the programmatic, or where you are actually trying to encode some of these behaviors as opposed to learning from data? Do you think they are completely, it's everything should be data driven, or is there a significant role where those methodologies can help with?
I think maybe I'll jump into one of the key ideas of one of my sections, which was trying to split the problem into blocks that are solvable, and also having like high level and low level like policies. I think that symbolic approaches might be useful for there are some things that we don't want to learn, some things that are simply we don't have to learn very low level actions related to the camera's movement in space, because we do have great optimization based models that can do that. But we do want to learn kind of like higher level decisions that depend on the context. I think that's where machine learning can play a very important role. At the same time, I think symbolic approaches can be used to create some structure for the machine learning, for machine learning. So instead of trying to learn everything, let's say in a model-free fashion, we could create, let's say for the movie language, like usually you have certain transitions that happen with the camera, like either on the like actual physical camera movement, you go from like this type of shots to that one, and then to a third one, or even in terms of the storyline, you have like like usually you have certain transitions that happen in terms of the script. So I think we can use explicit symbols to encode those transitions, and then we just try to learn, let's say, the probabilities of transitions. I think that's a good way of combining both approaches.
Okay, great. Thank you very much.
Yeah.
Is it my turn?
Sure.
All right. Really nice presentation. Really great breadth of work. I had a couple of questions. Maybe something's a little bit more on the clarification side. So for the semantic descriptors, are these sort of continuous values that you're providing it? Or yeah.
So they can be continuous values. You would basically say that you would, like, on the generation side, on the generative model, you would basically say that you want to provide you want to create a clip that is so you have we have 7 descriptors, so we have a 7D vector, and basically you provide the value that you want for each one of the descriptors. It can be a continuous value. Usually you would go, let's say, for how exciting a clip is. You would say that you want to make a clip that is within, let's say, 2 standard deviations of being exciting. So that's a like highly exciting clip. For the other parameters, you can many of those parameters are correlated with each other. So
right.
Let's say if you only care about how exciting the movie is, like you would set the excitement parameter in a continuous way, and all the other 6 parameters would be
right. Yeah, the Gaussian conditioning in there.
Yeah,
I guess I was just kind of wondering, like, if you said, okay, I want this to be very exciting and very calm at the same time, how does the system react to that?
So that is allowable, but the problem is that you would fall into a region of this space of emotions where we never have data, or very likely we will never have data about a movie that is both very exciting and calm at the same time. So I think you have some garbage output out of the model if you try to do that.
Okay. Did you ever try it, like different combinations to see what kind of emotions it tends to, like? I mean, I can also imagine that one of the emotions becomes more powerful.
Yeah, so I tried, like, for the paper, I only dealt with, we have a lot of like evaluations of actual user study evaluations to see if we actually achieve the desired degree of expressiveness of each emotion. But I only tried with one, like only doing one emotion at a time, and all the other 6 were just conditioned on the first one. Just to like fool around, I did play with a couple different emotions, but I didn't go so deep into this details to see if one emotion prevails over the other. Okay. I don't know any like quantitative details on this.
Okay. On the sim to real transfer, so like in what we've shown, so largely all the obstacles are these red squares, right? So you have this sort of in simulation and this sort of these constructed red squares in the real world. I was just kind of imagining, if this was a course in a wooded area where you would have, a variety of different obstacles, how well would that work there? Would you sort of incorporate it there directly? Would that be a second subsystem for these different kinds of obstacles?
I think we would have to, if we had let's say if we trained on a regular simulator and then we tried to deploy this in a forest with red gates, very likely we would. So the network never learned that it should not so the network only learned that it should go towards the red gates, but it never learned to avoid other things necessarily. So very likely in the wooded area it would potentially crash into the trees.
But if you trained it, would you sort of recommend training it with different trees in simulation then, or?
Yeah. So I think something that we would probably have to encode in the simulator is something that helps a lot is to put those additional losses on the latent space. So if I were to train this, maybe following the same approach that I did for the gates, I would likely also encode the positions of the trees as additional losses coming out of my latent space. So that, the drone could learn by itself to avoid the trees. But what we noticed on this paper was that by putting those explicit additional losses to train the representation, it will learn much faster that this is a tree and I should be avoiding those types of trees. Yeah.
Okay. So one last question, and this is kind of going into sort of ethical implications of research. I mean, you've developed here a drone that can follow people. I assume in this case, all the people want it to be followed. It can reason about occlusions. I could definitely see some sort of, nefarious applications like stalking, following people unwanted to. Would it be easy to use this for those kind of applications? Is there some way to sort of avoid those kind of applications?
Yeah, I think it depends on. I mean, maybe what I'll say is a little commonplace, but no, this is just a technology and it can be used for good and bad. It will depend very much on who is deploying the system and what are their intentions. I think, from a this is a very general way of organizing the problem, like occlusion avoidance, but occlusion avoidance can be used for evil or can be used for noble purposes. I think we, as researchers, we just have to choose the kinds of problems we want to be working on and what we feel is the right thing to do. I think it's a very subjective answer.
Okay. All right, that's my questions for now. Thanks.
Thank you.
So I can ask my questions now, if that's okay.
Yes.
So I wanted to go back to the question that was asked earlier about, about creativity and composing shots. So my memory of the middle project that, which I was involved in, so hopefully I remember correctly, was that you designed a lot of trajectories in an attempt to span the space of generating possible emotions. So you had all of the different standard kinds of shots, following shots, and so on. And then you tried to span the space of a set of parameters for those. What I think maybe that project was missing was the ability to have a new form of happy shot or excited shot or whatever. Because all we could do was discover the labels for the shots that we had started out with. So first, is that correct? And second, how would you perhaps address that limitation?
Yeah, I think what you said is correct. Since we're using a data-driven machine learning technique, what we identify as being a happy shot we'll only know what's happy based on what our data set tells us that is a happy shot. This follows from because we're using supervised learning here. Maybe as a way to address this type of problem is we could, I'm thinking out loud here, but one possible way in which the concept we need to implement is to give some randomness or give to find out some new types of shots for the system. Let it have some artistic freedom to experiment with new parameters. So I thought maybe if we apply a technique such as reinforcement learning, but the problem there is we would need to have some well-defined reward function. There's some work in literature on trying to explore new environments, for example, in physical spaces, but maybe we can have some analogous function for the emotional space and try to explore areas of emotions that haven't been touched before. And then we'd have to generate these new types of movements, but we would still rely on the humans to label those emotions for the supervised learning system. I don't know if maybe it was a little convoluted of an answer, but yeah, we need to input some randomness into the system to generate new shot types.
Yeah, I'm not sure if I believe that randomness would work because it's too high dimensional a space. I think, well, I think there are other ways you could go at it. You could try and learn it from existing movies or other sorts of things. So you could potentially try and bootstrap your way to other kinds of ways to convey those emotions that way. So we spent a lot of time trying to figure out what the emotions should be that we wanted to convey. I'd be interested in hearing your thoughts on, suppose we wanted to do twice as many emotions as we did. How would we go about expanding the work to handle that? Or maybe 10 times as much is even a better question.
Yeah, that's a good question. I began with a much larger list of emotions. Maybe I had about 20 to 30 emotions at the beginning. I cut a lot of them out because they were, for example, not applicable to, we were looking at a very limited scope of kind of 20 to 30 second clips. So a emotion such as being dramatic is not something that applies to our context because we're only dealing with the movement of the camera in space. And it would be hard to convey the emotion of a dramatic movie by just changing how we move. There are many adjectives that I also cut because they had to do with a larger plot of the movie, so like longer time steps, or they had to do with sounds. So I think to be able to use more emotions, we would have to consider a larger scope of what our movie comprises of. So like larger time lengths and maybe with sounds or like a more complex action space. So that's the first thing. The second, which I see as being a bottleneck of the current approach, is once we have more emotions, we will require a lot more labels, especially if we try to follow a pairwise comparison labeling scheme like we have right now. It grows kind of with size n log n of the number of emotions you have. So I think if we were trying to have, let's say, 100 instead of 7 or 15 emotions, which was the scope that we had for this project, if we wanted to have 100 or 200 emotions, we would very likely have to come up with a better data labeling scheme, perhaps going to getting absolute scores from users instead of doing a pairwise comparison, because it would just be much more data efficient, or some other approach. But something that I think I would not scale the current approach to hundreds of emotions.
Okay, and my last question in the sim to real part, that trajectory is not very aggressive. It's much less aggressive than what you would see in the drone racing world. So, and usually the differences between the simulators and the real world show up as you are more aggressive about the parameters that you're using, the dynamics becomes more complicated and so on. So I wondered if you could talk about what you think would happen if you tried to use a much more aggressive course or much higher speeds.
Yeah, it's something we initially I thought that. So I think that question has a lot to do with the type of representation that we have. The representation basically tries to sum up all the state information that is necessary for us to compute the velocities, the control policy. With the current speeds that are involved for this drone racing task, we have a relatively simple state space. So it just takes into account the current RGB image from the camera, and that's what we use for computing the velocities. If we were flying much faster, I think that one thing that we would have to include there is some sort of recurrency in the network for the representation, because it will not only matter which kind of image we're seeing right now from the camera, but it also our velocities matter a lot more if we're being much more dynamic. So that's something that I would include in modifying the current approach for faster speeds. Also, something that would be relevant here is we would have to make sure that the simulator dynamics are much more accurate, because of course errors in the simulator would then translate to some different behavior in real life, especially if we're trying to do very aggressive turns. So those are the two things I would really try to consider.
Okay, thank you.
Thank you.
I think maybe Rogerio, just to clarify, I think another kind of limitation is I think you always have to see the gates, right? And I think the camera was relatively narrow in view.
Yeah, it's something we struggled with when we first transferred the policy from sim to real. We had a camera with a quite narrow field of view of, I think, 50 or 60, one of the Intel RealSense cameras. And that was an issue because, yeah, quite often we would just not see the gate. And then when that happens, depending on how we train the system, let's say if we train the system to only do clockwise race courses, then it would have some implicit bias. So the drone would tend to always turn to the right side if it didn't see anything. But if we, in the end, we took an approach where we could run either clockwise or counterclockwise. We had data for both types. So there was no bias. So if it didn't see anything, it would just keep on going on a straight line. Camera to a wide field of view, train the system again in simulation, and then deploy it in real life. And that was much better.
Okay, so I had a couple of questions as well. So I think one is, so in some sense, the approach has a lot of, decomposes the problem into some modules that essentially talk to each other. Right? The planning, there's the motion, and so on. So are there some situations where there are unintended consequences with this kind of separation between the modules, or some unwanted interaction?
Yeah, for example, one type of unwanted interaction is that sometimes errors kind of get cascaded, or sometimes you get a positive feedback loop of errors. So in the case of the drone cinematography project, at some point we had some issues on the mapping system, which basically the height of the drone was not so accurate, which in turn caused an issue on the detection of the subject. And then the drone would tend to kind of move further up, and then it moved quite aggressively, and then the height got even more messed up. Then it would go lower because the projection of the actor in the word frame would go further away, and then you would see this kind of bouncing behavior because we had very explicitly separated components in our pipeline, and we had an issue that created a positive feedback loop. So that's an example of unintended consequences.
Okay, and then kind of building a little on top of this. So in some sense, part of why the system works quite well right now is that you have chosen some good abstractions to learn. Right? Like, for example, the representation of your view angle, distance, and there's basically implicit, or I mean explicitly, you define some models and some abstractions that you learn on, and that's I think part of why it generalizes quite well, right? Is that true? I mean,
I would say so. We did spend a lot of time trying to identify what are those, what is this minimal set of parameters that identifies that can express the movement of the camera, that is both applicable to the language of the movies and that makes sense from a robotics perspective. And so I did spend a lot of time trying to think of what is the best abstraction for the action space, for the state space of the drone as well, that encodes all of this for the movies and for robotics. So yeah, I agree with your statement.
So then, let's say we would say, hey, let's throw that all out the window. Those boxes are artificial. We just made up these parameterizations. Who knows if that is the best thing? And essentially try and do, let's say, some end-to-end learning. Run in ASM for a couple of years, and then come back and say, here's the perfect system. So what's what's kind of your opinion on this?
So I have two major concerns with this type of approach, and I think The first one also relates to Jessica's question before, and it is that we're dealing with a very high dimensional space. So the position of the camera can be anywhere in space and can be changing to anywhere else that is dynamically reachable over time. And any combination of it just like grows exponentially, and there's no bound on how complex the movement of the camera can be. So that's one huge point of concern. And the other one that also makes this problem hard is that our evaluation function ultimately depends on human evaluation. A good movie is only good because we as humans say that it's good. It's very hard for us to define like some cost function that defines the goodness of a movie. So beyond, besides having a very high dimensional space, we can't like obtain rewards. Like we would have a human being the bottleneck for the reward scoring system for such a system. So those are my main two concerns.
Okay. And then I think another question I had is kind of related to what Jessica was saying also, is that initially in the project, like very early on, we were discussing this idea of, hey, let's say we crawl YouTube or show good movie examples and try and learn some action function from those, right? And then we kind of went away from that to essentially use this kind of abstraction of view angle and shot as kind of the parameterization, and then I guess you looked at the semantic policies there. Can you now kind of looking in retrospect, do you see a place of where this type of data could fit into the system?
I think, so lately I've seen some works in literature that try to learn, basically they try to learn latent representations of camera movements relative to the actors. And I think this has a lot to do with, and they do this by observing long sequences of movies like Hollywood movies, for example. And I think that's almost a middle ground between what we've done in terms of very explicitly modeling the parameters of relative positioning and trying to learn like these more abstract models of for the actions of the vehicle. So like trying to learn this latent space that is neither 100% hard-coded in terms of like what things mean, but is also not completely free. Like that could be a good middle ground to join both sides of the equation.
Okay. I think this is good for now. Nathan, you wanna guys have any, or we don't have to go in order. If you have some more burning questions.
Yeah, I have one comment and one question about the last project. My one comment is about it could be interesting to think about more specifically the application that you've presented, because you span from directors and trying to create good cinematography and stuff, to being able to have a very high level interface, which would be more like for a layperson. Like if they had a drone or something they just put out there and they just say, make an exciting shot, and then I'll just do it. But one reason I think why directors like, very meticulous control and 3 people on the same things, because they want very specific shots of the view. So they might say like, come around the person, then zoom in aggressively or something like that. And so it's a combination of like these terms, but also high-level geometric descriptions and things. And it might be interesting to look at things like what that language is. It's kind of getting back to my original question, but also how you might use like inverse optimal control or something like that to extract the different parameters of that and actually create like little skills or somehow be able to map from that language to the control system that you've designed. So that's my comment. My question is on the last part. So that's all about simulation to real, and just kind of like digging into the scientific nature of that. You showed basically that you can do this thing in simulation and that it generalizes to the real world in some different lighting conditions and stuff like that. But how would you go about characterizing how well that works? So how well it generalizes to these real world situations, and then kind of breaking that down into where is error coming from and how might you reduce that?
Yeah, I do have at least a partial answer to your question. Let me try finding I had some other backup slides here that do show some quantitative results for this experiments. Just 1 second. I guess you can see the new slide. So to quantitatively evaluate how well our particular approach for learning representations is better or worse than others, I did test with a few different types of representations. So let me explain. I think there are a lot of names here. So on the x-axis we have basically the difficulty of the track from zero displacement. They are perfectly aligned on a circle, up to 3 meters of displacement. On the y-axis, we have the performance that we say that I think if the drone goes through if it can complete 3 entire courses, then we say that it's 100% performance. And if it's less, then it's just the proportion to that. And I tested multiple methods of different representations. The first two are basically variations of our the cross-modal VAE architecture. The second one in green is just using regression to basically regressing from the image to a velocity directly. Or sorry, it was like using only using the gate pose as a information for training the representation. The fourth one in red is the direct end-to-end regression. And the fourth in purple is using a vanilla VAE architecture just with image reconstruction. And these are the results in simulation itself. So trained and tested in simulation. You can see how like already in simulation, the architectures we proposed perform much better. Then we did have some results in, here's a video basically illustrating what I just explained. But so we show for different difficulties of the track, how our method performs in comparison to end-to-end learning or a vanilla VAE. And then for real life, I got the best performing models from simulation, and then that's the ones that we evaluate in real life. So we have 2 circuits, the circular circuit and the S-shaped track. And we can see that our model can go through, for example, on the S-shaped track, out of 8 gates, we can go through 7.8 gates on average, or like we can go through 14 gates on average for the circuit, while others, like the one that uses regression, which does quite well with simulation, like does really poorly in real life. So I mean, I think that.
Sorry about that. This is about comparing your technique to other techniques and how in this performance in the real world. But how would you characterize the degradation of performance from sim to real? Yeah,
I think what I observed in our experiments was, in simulation, like for example, for the track with up to, going back to this plot, I think maybe what I could also try to observe is, maybe make a similar plot like this, but comparing the best policy in simulation, its performance for different amplitudes of gate displacements, and have the same thing for the policy deployed in real life. And we could see the delta, and the delta would mean, would show us the degradation of the policy from sim to real. I think that would be an example.
Yeah, I think that was another thing that I'll point out is that the simulation can be very diverse. Like there's a lot of domain randomization techniques and stuff like that, but even beyond that, you can change the lighting conditions and things just to have a holdout set of simulators that you've never seen before, and then simulators that you've trained on, and see if you can measure that and see if that correlates with like deployments in the real world too.
Yeah, it's something that so I didn't use domain randomization because what I was trying to observe was just I think my technique could also be used with the domain randomization. They're not mutually exclusive. But yeah, for future work, I think it's a great idea to even make it more robust using domain randomization.
Mm-hmm.
Yeah, and I think we could even dig a little deeper in terms of like, you know, what I guess you could look at if you had a graph. I guess you're essentially looking at the relative gate position or something like this, right? Is essentially the output. And we could look at if you would take a data set with some ground truth of that gate position, and essentially we can look at the fit error as we vary the background in some sense, or you know, even do some maybe adversarial things.
Yeah, it's a good idea. We didn't have a ground truth real life gate data set to compare with, but you're right.
Questions?
Should we open it up to the
Sure.
whole audience, maybe?
Yeah.
I do have a question, if I may. So, first of all, congratulations. Good presentation, and you're pretty amazing. I have a question regarding like the middle projects, the one that are trying to identify emotion from video, from camera positions, right? If I understood it correctly, in one of your projects, you showed them the same video clip, but changing the same scene basically, but seen from different positions, right? And then you ask them to rate them, you know, on a scale. So which one is more exciting? This one is more exciting or more sad and whatnot. But the question is, not all scenes correlate to all feelings, right? It also relates to content. You can show a puppy being stabbed, and you can. It's very hard that someone's going to say that's happy, right? Regardless of how well the camera is moving. Or you can watch paint dry under several different camera movements, and it's still going to be paint drying. So the question is, do you think that's an essential limitation of your work, and how could you address that limitation? Like, how could you include a bigger diversity of scenes? Do you think that would improve your emotional summation?
Yeah, I have a very good question. And in a way, we purposely chose a scene that is relatively neutral in terms of the emotion that the underlying scene has, like just a person that is going through a suburban environment with like some cars. So it doesn't express, just by watching that scene by itself, it's not super exciting, it's not super boring, it's just mild. And then we were trying to see how the camera movement itself changes the perceived emotions. But as you said, we could very well have tried to condition. I think in terms of machine learning, you could try to think of conditioning. The emotion will be conditioned not only on the camera movement, but also on the underlying scene. And we could explore this method to multiple types of scenes. It's something that we did think about when we were first formulating this problem. One reason why we're not really conditioning on the scene right now is because that would significantly increase the dimensionality of the problem. And we wanted to solve a simpler problem first, just even see if it works, since it was something quite different from what anybody had done before. And once we show that, yeah, this can work, I think now we can think of next steps in conditioning on the scene itself.
Yeah, the reason I was asking that is because when you're comparing things that are not relevant, right? So say you're comparing a scene of a puppy being stabbed, and you ask, oh, is this happier or is this more exciting? I would say it's none, right? So the comparison when the scale is that is kind of null, right? So if you're watching a scene that is neutral and it doesn't really inspire any feelings, the comparison there is basically just noise. Did you observe that you had a lot of comparisons that were somewhat sounded like random shots. That's what that's.
Yeah,
that's
that's expected that we will have some comparisons are we force people to choose left or right, so it may be the case that there's some noise there. I did verify, so I did have a model of like I simulated, like before deploying the user study, I had to understand it first of all, like how many samples do I need, or how many comparisons do I need to obtain a good score. So I actually had a ground truth data set that I like a synthetic data set. It was not of like possible scores. And I did some simulations to understand like how many, like depending on the noise level of my comparisons, like how many, like what is the number of comparisons that I need in total to obtain a good final score to overcome the noise. So I did study this aspect of the problem. So we have Samuel Clark, who's also raised his hand.
Thanks, Rogerio. I was curious, I mean, in directing, you're often like doing a retake. So I was curious, what all can one of these systems, or just like a generic robotic cinematography system, learn from a retake? Like maybe in terms of planning, you don't need to remap where the trees are, et cetera. And then in terms of feedback from the director, et cetera. And how would you go about incorporating that into what you have here or into something new?
Just to clarify, when you say a retake, do you mean like going to an environment where I have already filmed a scene before and I know all the features, or do you mean something else?
Yes, and maybe even it's the exact same scene. It's just they didn't quite like how the camera was oriented in this shot or something, and they want a slightly different take.
Yeah, I think in the current system setting, you would like we have like different interfaces, right? Like one where you specify those parameters in terms of the language of the movies. So in that case, the director, they could themselves specify if they didn't like the first scene, they would specify a different distance to the actor, the scale, the line of action angle, and the tilt angle, and the drone would just execute what the new command that they sent. On the other interface, based on semantics, to change, if we like deployed the same thing, the same model, on the same scene, we would have the same behavior because it's not a stochastic. And to actually have a different behavior, we would have to get new training data into this model with the new labels that the director thinks that particular scene is not exciting. Then we'd have to generate new clips with the same parameters being not exciting, retrain our model, and then deploy that again. So I think that would be the cycle of production.
Okay, and is that the way you think it should be done, or do you think it should be done another way?
I think the way it should be done is a easier variant of the second approach that I said, or maybe like as Nathan said, it depends a lot on like who is deploying this robot. If it's an amateur user, like usually just doing the average thing is good enough, and they just want to make an exciting clip, and whatever it comes out is mostly good. If you're just going, let's say, snowboarding with your friends, like you don't really care if you like exactly what the angle of the drone was. So the average thing is good enough. But if you're a professional director, then you truly care about the super low level, like the exact angle and the focal distance and all these things. So you're on the other extreme of deployment. Maybe for the average user, something in between, like just some like faster way to input new data into the system on the learned model, that would be ideal. But yeah, that goes into the production side of like if this was an actual product, that's how you'd make this interface.
Thank you.
Okay. Yeah, thank you everybody for attending Rogerio's defense. I think maybe if the committee could stay behind, could have a quick conference, and then if you're not on the committee, please drop off. Thank you.